already. Alright, so applications with radian measure using arc length of a circle and area of a sector. It's just two formulas, just using the formulas. So reading the questions, figuring out what part of the formula we have, putting it into the formula, and then solving for the thing that we don't have. Okay? So just as a quick review, so arc length is going to be measured, or is going to be the length of the arc of a circle intercepted by an angle. Okay, so when we take an angle and we draw a circle, that distance around the circle measured in radians is the arc length. Okay, as a reminder, the radians kind of changes as the circle gets larger as far as what one radian is considered to be. Secondly, because we are measuring arc length as part of radians, both formulas that we're using will ask for an angle measure, and it has to be given in radians. If they give you an angle measurement in degrees, you must convert it into radians. Secondly, actually no, that's not going to be an issue. So, you must make sure that your angle measurement is given in radians. Okay? Our first one for arc length, the formula is S equals RO. S stands for the arc length. S is the measure of the arc length. R is radius. And then theta is our angle degree in radians. So if you multiply the radius by the radians, you get the arc length. It's a very simple, straightforward formula. SRO. Alright, or sorry, theta really. So a couple quick examples here. We could be asked to find kind of any part. We could be asked to find the measure of the interior angle. We could be asked to find the measure of the arc. We could be asked to find the radius. It's all just plugging into the formula and then solving for the variable. So we'll start with finding the length of the arc. So our formula, SR theta. A circle has a radius of 18.20 centimeters. Find the length of the arc intercepted by a central angle with the measure of 3 pi over 8 radians. Right? What parts of that formula do I have given in the problem? We've got theta. What else? And the radius. I've got theta, and I've got the radius. Do I need to change theta? No, because it's in radians. So we just plug it in and we evaluate. The measure of the arc length is the radius, 18.20 centimeters, times 3 pi over 8. And we're going to round to 2 significant digits. So 18.2 times 3 pi divided by 8. Round to 2 decimal places, what do we get? 144. Pretty straightforward. Couldn't make it any easier if I tried. Our second circle has a radius also of 18.20, but we want to find the length of the arc intercepted by a central angle with a measure of 144 degrees. What parts of our circle what parts of our formula do we have?
Well, you have.
We've got radius and theta. Do I need to change theta?
Yes.
Yes. Okay. Theta is given in degrees, so we need to change it to radians. And again, I want to note, okay, here, so we have the degree symbol, so clearly we know it's going to be degrees. All right. But I want to emphasize something. On the left side, it said 3 pi over 8 radians. It does not have to say radians for it to still mean radians. Okay? It could just say with a central angle with a measure of 3 pi over 8. Because there's no degree symbol, again, it's assumed to be radians. So make sure that you're very, very careful with that. Just because you don't see radians doesn't mean it's not radians. If you don't see a degree symbol, then it's radians. So how do I change that 144 into a radian measure? Pi over 180. We're going to want to use the exact value. Do not round it until the end. Okay? Do not round it to the end. I actually saw that a few times on the last test with some of the trig functions, rounding too early, and then using those for cause you to be off by 1. So you want to keep that as an exact value until the end. So you can always simplify your fraction, 144 over 180, reduce your fraction. So our theta is 4 pi over 5. Then we can plug it into our formula. So radius times 4 pi over 5. 18.2 times 4 pi divided by 5. Round to 2 digits, what do we get?
57.18.
Okay. So there's our 2 arc lengths. So given radius and the angle measure, as long as the angle's in radians, we multiply them and round as appropriately. Okay. So putting it in some context, we've got lines of latitude and lines of longitude that go around the Earth, and those are based off of the degrees of a circle. Going from the center of the Earth. So Reno, Nevada is due north of Los Angeles. The latitude of Reno is 40 degrees north, while the latitude of Los Angeles is 34 degrees north. The radius of the Earth is around 6,400 kilometers. We want to find the north-south distance between the 2 cities. Okay, so we're trying to find an arc length because the Earth is a sphere. We're trying to find that arc length right there between Los Angeles and Reno. Okay, we're given lines of latitude which are based off of the entire Earth. We've got 1 degree and 2 degrees and 3 degrees and 4 and all the way up. So Los Angeles is at 40 degrees latitude and Reno is, 34, and then Reno is at 40 degrees latitude. Okay. We need to know the difference between those for the angle measurement. We're not going to use the full 40 or the full 31 or 34. We're just going to use the difference between the 2. Well, how far apart in degrees is Los Angeles and Reno? 6. How do we know that? Yeah, 40 minus 34. So the difference between the 2 gives us that angle measurement of 6 degrees. Okay, so we have theta as 6 degrees. What else do we know? Yep, we've got the radius as 6,400 kilometers. 6,400 kilometers. All right, do we need to change anything before we plug it into our formula? Yep, we need to change 6 degrees into radian. So what is our radian measure? Degrees is pi over 30 radians. Find our arc length. Round to 2 decimal places. What do we get? This is the last problem. I hadn't done it. 670.20. 21. Pi times 6,400 divided by, well done, 670. Okay, 670.21 kilometers. That's how far away Reno and Los Angeles is. Okay. All right. So here we have a rope being wound around a drum with a radius of 0.8725 feet. How much rope will be wound around the drum if it's rotated through an angle of 39.72 degrees? So again, we're looking at the outside. So anytime we're dealing with a word problem that is the outside of a circle, that's arc length. Okay. Next, we're going to be doing area of the sector. So whenever we're looking at area of something, then that's going to be the area of the sector formula. So you just know the difference between, are we doing with the outside or are we doing with the inside? Outside is going to be arc length. Inside will be area of a sector. So we have to think about what we know and what we don't know. What do we know? What's my radius? 725 feet. Okay. What else? That's what I'm solving for. I know theta. I know the angle measurement. So we take theta, multiply it by pi 1/80, so we're in radians, and then we multiply. How much of the rope do we get? Zero 0.6? 0.6?
Oh, yeah.
0.60. If we want to do 2 digits, it would be 0.60. We're dealing with significant figures, level of accuracy. Alright. Alright, this one's going to be a little more involved. So 2 gears are adjusted so the smaller gear drives the larger one. So as the smaller gear turns around, okay, over and over and over, the teeth push it and rotate the larger one around and around and around. Alright? So because the gears are different sizes, the gears will rotate a different amount as far as the angles are concerned. Okay? So a smaller rotation on the bigger gear has a larger impact on the smaller gear. Okay? So the angles will be different. Okay? But because radians measures that outside arc length, if I rotate 1 radian on the smaller gear, it's going to be the same linear distance on the larger gear. They have to match up. Okay? So what we're looking at here is that if the smaller gear rotates a certain amount, we want to figure out how much the larger one does. So we need to first find that radian measure for the smaller gear, and then use that same radian value to find out the degrees of the larger gear. So we're going to find the radians first on the smaller gear, and then use that to find, and use that as the same radians in order to find the angle measurement on the larger gear. So we'll start with the smaller gear first. Alright, we have our radius. What's the radius of the smaller gear? 2.5 centimeters. And then what is our theta value? What's our angle? 225. Okay, use pi over 180 to convert it to radians, since we're dealing with degrees. We want to convert it to radians. Okay. So what is our arc length on the smaller gear? .82. Okay. So we rotate through an arc length of 9.82. The larger gear rotates through that same arc length. But because its radius is different, the degrees will be different. The larger gear rotates through the same arc length. rotate the same amount. 9.82 centimeters rotated through. We need to use that same amount, but now with the radius of the larger gear. What's the radius of my larger gear? And we don't know the angle measurement. So given the arc length and the radius, algebraically, what do I do to find the angle measurement? Divide by 4.8. So we take our 9.82 and divide by the 4.8, and we get theta as 2.05, approximately. Okay? So, did we rotate through 2 degrees? It's in radians. We rotated 2 radians. Now I get 2 degrees. So what do we do? Multiply by 180 over 5. So 2.05 radians times 180 over pi. So we get approximately 117.2 degrees. It's a simple idea, but it's something that has big implications. You have to remember that theta is in radians. So you either have to use a value, or if you're finding theta, remember that it's in radians. And usually, problems don't want the answers in radians, they want degrees. Okay, because radians is pretty relative, but degrees is something a little bit more concrete that is consistent from circle to circle. Okay, so 117.22 degrees. All right, last thing we're going to cover is the area of a sector of a circle. So we got another formula here. The sector of a circle is a portion of the interior circle intercepted by a central angle. Think of it as a piece of pie or a piece of pizza, okay? It's a wedge. It's that wedge shape that's rounded. And so we're actually taking, very similar to the area of a circle, okay, pi r squared, but we're adjusting it slightly where it is 1/2 r squared theta, okay? Again, theta has to be in radians. So finding out what information we have and then solving for whatever it is that we have left to find, okay? So pretty simple. There's not a lot of real-world application with area sector, but there is some. We get some oddly shaped things that we want to find the area of. But it's just plug and chug into the formula. Our area is 1/2 r squared theta. Okay. So given this wedge-shaped field, okay, what information do we have that we can use in our formula? Okay, what's theta? Okay, 15 degrees. Can we leave it or do we need to change it? We need to change it. So we'll have to multiply by what? 180. Pi over 180. Okay. And what else? The radius. What's our radius? 321. So 1/2 321 squared times 15 pi over 180, our theta in radians. And what do we get? $13,400. 488. So there. Let's double check that. Not that I don't believe you. That's why I'm double checking, because you didn't seem super confident. So let's find out. 180. Hey, look at that. Good job. 13,488. And then we'll just leave it at that. There we go. Yep, that was it. 2 formulas. You don't even have to memorize them. You just have to know which one's which. Okay, S is your arc length, A is your area. Pretty straightforward. Questions, comments, concerns, queries, conundrums. All right. So